Hey everyone, today I want to talk a little bit about cross products because I've referenced them so much in my other videos, but I haven't made like an official one which goes into extensive detail about what they are, so I figured I might as well do that. So to get us started, I'm going to talk about determinants. Let's start with the raw definition. If we have a matrix that goes A, B, C, D, right? The determinant, which I'm going to use these bars to represent, is AD minus BC. The problem is that's a very forced and ambiguous, vague definition. So let's discuss this in more detail. For this, I'm going to create a picture. In this picture, I'm going to throw some vectors down. One vector is going to go to the point 3, 0. So 3, 0. And another vector is going to go up to 0, 2. Alright. Now, we can write each of these vectors instead of in like this row. How about we write them each as a column? So like this 0, 2 becomes 0, 2 like that. And this 3, 0 becomes 3, 0 like that, right? So there is our x coordinate, there's our y coordinate. Right? And what we could do is we could go ahead and list these out like in a list, go 0, 2, and 3, 0. And those are our two vectors. Or we could just end up combining them into one matrix. Like that. Right? And so we've written out two vectors just as a matrix. Now, let's go ahead and come up with a conclusion already. And let's calculate the determinant of this. So the determinant of this matrix is -6. Right, just based on the above formula. Well, that's interesting. If we form a rectangle with these two vectors, right, what we'll find is that it has a height of 2 and a base of 3. And if we wanted to find the area of this rectangle, the area is just 2 times 3, the base times the height. So we get 6 and -6. It's almost like the magnitude of this determinant is the area of that rectangle. That's a very interesting fact. Let's see if this extends further. I'm going to make, instead of a rectangle, we're going to make a parallelogram with these vectors. Let's draw this out. Boop. This time, I'm going to use the vectors. We'll do 3, 0 again. And we'll do 1, 1. Okie dokie. So there is our 3, 0. And 1, 1. Alright. This time, we'll calculate the area first. So, that's the parallelogram that's spanned by those two vectors. Cool. So, we just need a base, and we need a height. So the base, I'm going to get rid of that fill-in, right? This perpendicular distance is the base, and here's our height right there. So our base is very clearly 1, and our height here is very clearly 3. So our area of this parallelogram is 3 times 1, which is just 3. If you don't like parallelograms and you really want to break this into triangles, this is 2 triangles with an area of 1/2 and 1 rectangle with an area of 2. Alright, let's calculate this determinant. I'm going to throw it in a matrix, or throw these vectors in a matrix, and calculate this determinant. And what do you know? It's almost like we get an answer where the magnitude of this determinant equals the magnitude of the area that is spanned by those two vectors. What happens if we try to take the determinant of a non-square matrix? Let's talk about this idea, right? Because we've established that matrix is just a list of vectors, basically. So what happens if we try to do this? I'm going to make my vectors 1, 0, 0, and 0, 1, 2. Alright, we want to take the determinant of that. Let's graph these out, and this time we're going to need 3 dimensions. There's my X, Y, Z. Alright, so we go out 1 in the X direction. Go out 1 in the Y and up 2 in the Z. Alright. Now, the interesting thing is if we go ahead and make a parallelogram out of these two vectors, right? This is sort of awkwardly shaped. That's a little better. Alright, there's our parallelogram, right? We have this flat image in this 3D space. Flat. Right? And so, why couldn't we just map that parallelogram into a 2D space, right? That would be the ideal way to tackle this. So instead of having 3 dimensions, we should just reduce this down to a 2-dimensional plane. And the result of this is that really we're trying to think of a volume computation as we're trying to apply a volume computation to a flat surface. And what I mean by that is, let's say that we actually have 3 independent vectors, right? I'm going to go 1, 0, 0, 0, 2, 0, 0, 0, 3. Okay? Right? Well, now if we have 3 of these vectors, so let's make a picture and compare and contrast this. Right? So we've got 1 out in the x direction, we've got 2 out in the y direction, we've got 3 out in the z direction. So these 3 vectors, they end up making, right, a rectangular prism. That's what they end up spanning out. Right? And that is appropriate for the amount of space. Right? We have 3 3D vectors. If we have 2 3D vectors, we end up getting this flat shape. That would be better if we just mapped it to 2D space and turned, you know, a 3x2 matrix, which we can't compute the determinant with, into a 2x2 matrix, is what the result of that would be. This, though, we have these 3 linearly independent vectors, so they make a solid shape that we can find the volume of in 3D space, right? And so, what we end up seeing, and you know what? I'm not even going to compute this determinant with the algebra definition. We know that if this is a 1 by 2 by 3 rectangular prism, the determinant of it is going to be the volume that's spanned by those 3 vectors. So it's a 1 by 2 by 3 rectangular prism, which is 6. So, right? So what we see is that determinants only work with square matrices. Because you need the proper number of vectors that fit in the space. Okay? And the function of a determinant is to find the area that is spanned by those vectors, right? Find the area or volume of the shape that they span. All right. So let's make this official, though, and define exactly how we would compute this 3x3 determinant, just so there's no ambiguity about that. So if we were to go 3x3, we'll go A, B, C, D, E, F, G, H, I. Okay, there we go. If we wanted to calculate the determinant of that matrix, so boop, make these brackets into lines. I'm so bad at remembering to do my notation right, or consistently, whatever. So that would be A times the determinant of E, F, H, I, right? So it's like we pick a top letter, and then that gets rid of this column, and we have to do this determinant right here. Okay? So that's 1. And then we go minus, and we do B. B will knock out this column, leaving us with D, F, G, I. Okay? D, F, G, I. And we'll go with plus C times, if we pick C, that knocks out this column. And we have D, E, G, H. Right? And this is just a rule to memorize. If you go further and further out, right, you can think of the signs of each term changing. So if there was a 4th column, it would be a minus term. If there was a 5th column, it would be a plus term, etc., etc. Okay, so now for this matrix, specifically, that would be 1, 0, 0, 0, 2, 0, 0, 0, 3, which would basically be 1 times 6 minus 0 plus, and then it just 0 times each of the whatever the other determinants are. And so you end up getting 6. Right? And so we see that this 3 by 3 determinant is in fact equal to just computing the volume that's spanned out by these 3 vectors. Okay? So now that we understand how to compute a 3 by 3 determinant, let's write out a cross product. So if we have 2 vectors, A and B, and we take the cross product of them, that's the same thing as taking the determinant of the following matrix. We put the unit vectors I, J, and K in the top row, and we put the X, Y, and Z components of A and the X, Y, and Z components of B in the 3rd row. And we just compute that determinant. That is the fundamental definition of a cross product. That being said, that's not very intuitive, so let's go ahead and do some examples. And since this is a physics channel, we'll do this with a physics example. So I'm simply going to have an XY plane. There's my x-axis, there's my y-axis. Let's be really clear about what these unit vectors are. So that is an I hat unit vector, points 1 unit in the x direction, and here is my j hat vector, points 1 unit in the y direction. Okay. So in this example, I'm going to put a particle somewhere, and it's going to have some linear velocity. And in fact, let's not call it velocity, let's just call it the linear momentum, just so it's simpler. There is also a distance from the origin to this point, and that's r. Alright, and we want to find the angular momentum. So angular momentum is simply the cross product between r and p. And so, in order to do this, let's go ahead and determine what each of these vectors are. And so my r goes 1, 2, 3 units to the right and 2 up. My p goes -1 x units and 1 y unit. Alright, perfect. So now, if we wanted to take the cross product, we would simply put these in a 3 by 3 matrix. Or, yeah, don't do the brackets. I need to keep catching myself on that. Just the lines. So we go I, J, K. And we go, what's my R3, 2. Alright, what's my Z value? What's in the K hat direction? Well, we're locked in a 2D plane, so we can very clearly see that our K value would ultimately be 0. And likewise, that logic would apply to my momentum. So we go -1, 1, and then 0. Right? And just to be super clear, what we're saying is that if we had some K hat unit vector in some third dimension Z, these go 0 out into that third dimension. Anyways, you know what? No, I'm going to leave that K hat vector there. And you'll see why. So, when we calculate this determinant, what we're going to end up seeing is that on our I term, that becomes 0, so we get 0 I hat minus, and we get 0 J hat. The only term that we get a non-zero value for is the K, in which we get 3 minus a -2, which is 5 K hat. So that is rather interesting. So we see that when we take the cross product of two things in the xy plane, we get a vector that is perpendicular to that plane. And that's our angular momentum. So that's one property of a cross product. That cross products are perpendicular to the two vectors being multiplied together. Another property, and we can very clearly see this if we just take a 2 by 2 determinant. So I'll go ahead and do that. Let's say that I just took the determinant of 3, 2, -1, 1, right? These are just the two vectors. Well, from what we've seen before is that when we calculate these determinants, that's basically solving for the area of the parallelogram that's made by those two vectors, right? And so if we do that, we end up getting 5. So by calculating this 2 by 2 determinant, we get the magnitude of the L vector. Right, we get that size. The reason why I'm bringing this up is because, well, if we agreed that calculating this 2 by 2 determinant with these vectors gives us the area of this parallelogram, and it's the same as this coefficient on the K term, then can we agree that this represents the area formed by vectors r and p, right? That parallelogram that they span out, we can represent the magnitude of its area with this 5 term. So that is another property of cross products. The magnitude of the cross product vector equals the area spanned by the 2 vectors being multiplied. For my final example, I'm going to introduce the right-hand rule. And we'll do this with torque, because torque is fun. Alright, let's say we've got a bar here, and on this bar we push it with some force F down. And this bar is length L. Okay. And we want to solve for the torque. So the definition of torque is simply the cross product between R and F, or L and F in this case. So F is very clearly just 0 in the x, -2 in the y. Our L vector is 1, 2, 3, 4, 5, 6 in the x, 0 in the y. Alright. And I'm going to write out the full 3x3 determinant. I'm not going to do this smaller determinant that gives us the magnitude. Let's not bother with that. Let's just use the complete full definition for this. I, J, K, and we go 6, 0, 0, 0, -2, 0, just like that. And the more you practice with cross products, the quicker they get. And we end up seeing that we get -12k. So that's an interesting result, right? Like if here's our k hat vector, I'll put all of my unit vectors back. Right, so if that's our k hat vector, our torque is going like that direction. There's our torque. Whereas before, it went in this positive direction, right? And so what's changed? What has changed? Well, these are actually 2 very different types of rotation, if you think about this intuitively for a second, right? Like this force here, you know, it sort of pushes with a rotation that looks sort of like that, right? Like in the clockwise direction. Whereas this particle, it sort of looks like it's moving in the counterclockwise direction, right? So we can see that they go in sort of opposite directions, just very intuitively. Beyond that, however, we use something called the right-hand rule to determine our precise direction without having to do all this cross-product stuff. If we do the cross-product stuff, it will give us the direction perfectly every time, no question, right? As long as we follow the rules. But if we don't want to do that, then instead we can find the direction by using the right hand rule. And in the right hand rule, what we do is the first term I'm going to just call A, the second term I'm going to call B, okay? Just so we can generalize this to any vector in space. So there's A and there's B. What you do is you stick your right hand out and you make each one point perpendicularly. So there's like your thumb, for instance, there's your pointer, and there's your middle finger. Right? And so what you're going to do is you point your thumb in the direction of the A vector, and you point your pointer in the direction of the B vector. Wherever your middle finger sticks out, that is going to represent the direction of the cross product between A and B. Right, so for this problem, and I'll use purple for the fingers. This is the direction that your thumb points. So we'll just call that T. This here is the direction that your pointer finger would point, so we'll call that P. And if you were to orient your fingers like that, you would end up seeing that your middle finger would point out this way, so that's M. And that's it. That's all the right hand rule is. It's just a simplification of this cross product. So you can use the right hand rule to make life easier, right? Because basically what that lets you do is, well, if you're using the right hand rule to figure out the direction, then all you need to solve for now is the magnitude of that vector. You know the direction it points already. But always keep in mind the math that it takes to get there. Alright, I've rambled on long enough. So with that, thanks for watching.